Hello mathematicians, we're now going to have a look at applications of integration of the reciprocal. So now that we have a method to actually integrate the reciprocal function, what it means is that areas under those curves, which are of course hyperbolas, can now be found by calculus, as can any volumes involving reciprocals of the square root of x. So what we have to be aware of is that we're dealing with a curve which has a discontinuity. So there are a couple of interesting things about it. One, which is just to do with the nature of E, is the recognition that if we find the area under either branch of the curve, basically, between the curve and the x-axis, between x equals 1 or minus 1 as the case may be, and E, then that area turns out to be 1. So it's another of the peculiarities of the exponential. The other thing is that while we can find individual areas either side of the y-axis, we can't find an area if we go from one side of the y-axis to the other side, because these curves run off to infinity. They don't cut the y-axis, they approach it asymptotically. So any volume from one side to the other is going to be infinite, or we'll run into problems of being undefined. So we need to be mindful of that, so a sketch of the curve is always important. So let's have a look at some typical questions. First one, sketch the region bounded by the x-axis, y equals x, y equals 1 on x, the reciprocal function, and x equals e. So as always, take your time and get a reliable sketch of what you're working with. So here we have that sketch, so we can see y equals 1 on x, we can see y equals x, we can see that we're going from 0 up to e, x equals e, and we can see that at this point here, we switch from the integral being the area under y equals x to it being the integral under y equals 1 on x. So obviously first task for us is to find the point of intersection. So that occurs of course when 1 on x equals x, multiplying across by our x. It's not an inequality, so no issues with that. We get x squared minus 1 equals 0, so x equals plus or minus 1, and clearly it's the plus 1 case that we want here. And we don't need the y value, so we don't have to work that out. The area then is going to be the integral from 0 up to 1 of x plus the integral from 1 on to e of 1 on x. And then they're two straightforward integrals. So that will be x squared on 2 from 1 to 0, log x from 1 to e, and when we substitute our values in, you can see that we're going to get 3 on 2 square units. The next one, we have a curve, y equals 1 on x squared, and it's rotated about the x-axis between y equals 1 and y equals 6. Again, your starting point should be a graph. So if we sketch that graph, even poorly, like I have, then this is our curve. The key thing is that we've got two positive quadrants, two positive branches of the curve, and that we approach the y-axis asymptotically. So this region here at least is an enclosed region or a defined region. We're going to rotate that around the axis. So because we're rotating around the y-axis, we want pi outside the integral of a y value to a y value of f of y all squared dy. So f of y of course means that we want x as the subject, and we want x squared as a subject in this case, so that's simply 1 on y, and away we go from there. That will integrate to log y, plug our numbers in, remember that log 1 to any base is 0, and we get pi times log 6. We don't evaluate these logs unless they're simple ones like this. We just leave them in log form because that makes it exact. So have a go at these questions out of 12D. Again, bear in mind what it is that's the big idea in this section in terms of applications of integration. remembering that any techniques that we've used before in integration are still applicable. We just have an extra technique now in terms of what to do with the reciprocal function, which integrates to a log.